In this video, I will derive the transformer turns ratio equation and the EMF equation of the EMF induced in transformer equation, or the EMF equation of the transformer. So, uh, what is, I will derive this from no basic, or from the basics, that is from the uh, Faraday's laws of electromagnetic induction. So what is the thing which you know, that Faraday's laws of electromagnetic induction said that the EMF induced, which we saw previously, said that E is equal to minus n d phi by dt was the EMF induced in any coil if the flux linking with the coil is changing. Flux linking with the coil is changing, and then the EMF induced was given by this equation. So now let us assume that we are having a core. So this is for the ideal case which we will consider, and we are assuming that there is a magnetic material which can be in the form of a core made up of steel or aluminium, etc., which will conduct the magnetic flux. And in ideal case, the cores are made up of stacked arrangement, but we are considering that we are having a core and there are two coils wounded. So there is a core, which is the first thing which we are assuming, and then we are assuming that we are considering that the core is having two turns. These are the copper windings, and this is also the copper windings, and that first turn, there is a two legs for the transformer or the core, and this can be in ideal case a core type transformer. So this can be n1 turn, and there is a n2 turn here, and I am applying a voltage V here. So V is given by Vm sine omega t. This is the equation of the AC voltage which I am applying. So this is only a single phase voltage which I am applying, and this is ideal transformer and this is a single phase transformer. So this is an ideal transformer, this is a single phase transformer, and this is a supply voltage which I am applying, and there is some voltage which I should get at this end, which is V2, and this is a V1 voltage. So it is seen that when I am applying the voltage, there will be a flux which is induced in this core. So again, this flux, if it is a value is phi, and the value of the flux induced will be a sinusoidal flux, and it will vary according to the applied voltage, and the current which is flowing through the primary winding will be I is equal to Im sine omega t. So the flux which is induced could be phi is equal to phi m sine omega t. So if this is my flux and which is induced, then according to the Faraday's law, then the EMF induced in the primary turn could be E1 is equal to EMF induced E1 is equal to minus N1 d by dt of phi m sine omega t. So this is equal to minus N1 phi m cos omega t. So this will be plus here after the differentiation, and the voltage induced in E2 will be is equal to minus n2 into d by dt, and the same flux will link with the second turn also. So it will be phi m sine omega t itself. So if I'm writing it here, then the EMF induced in the second turn will be E is equal to minus N2, and it will be plus N2 phi m cos omega t. So what have I got here is, if I'll just make some space. So what have we got here is, so what have we got here is the first equation. What have we got here is that we have got E1 is equal to n phi m cos omega t, and n1 phi m cos omega t, and the E2 is equal to n2 phi m cos omega t. So this is a voltage induced in the turn 1 or the coil 1 with n1 turns, and this is a EMF induced in the coil 2. So this is due to self inductance, and this is due to mutual inductance. So we can say that if we are dividing E1 divided by E2, then it will turn out to be N1 by N2, which is known as the turns ratio, or equal to A, or A, which can be written as A or small n, whichever symbol you are using. So this is known as the turns ratio of transformer. So my E2 will be equal to N2 by N1 into E1. So if I want to have a step up, that is increase my voltage, then I will need more number of turns at my secondary. So suppose my secondary turns are 1000 and my primary turns are 100, then I can step up the voltage, and my transformation ratio n will become equal to 10. So if my secondary voltage is equal to 10 times, suppose my primary voltage is 100, then my secondary voltage can be raised up to a voltage level of 1000 volts, which is equal to 1 kilovolt. So that's how it's possible to increase the voltage on the secondary side based on the primary side. So that was about the transformation ratio. And if you will see the equation of the EMF induced, there is something additional here which will come as part of the constant as a result of the differentiation. Is there is a omega will be added here, and again there will be omega will be added here. So it can be seen that it can be said from this figure that if you are having a transformation ratio, that is E1 upon E2 is equal to N1 upon N2 is equal to A for a ideal transformer. So this is a case where we are considering the transformer is having no loss, and no energy is wasted in setting up the magnetic field, or the magnetic losses are zero. So that's the ideal case. There is no loss. So if I'm saying that my current, the voltage which was the equation which I got, E1 is equal to Vm or phi m omega n1 cos omega t, and E2 is equal to phi m omega n2 sine omega t. So this was the equation which I got for the first and the second windings respectively by applying the Faraday's law. So what I can see is that if I consider this, then this will give what is known as my instantaneous value of voltage based on what is my time or what is my phase. So this voltage induced will be my supply voltage is also sinusoidal, my induced voltage will be also sinusoidal on the second side, and the frequency will be same, that is 50 Hz if the frequency of the supply voltage, and this will also be 50 Hz. And the equation of the EMF induced can be written as E1 is equal to Vm cos omega t, and whatever is my Vm here can be known as my RMS value, or this is my peak value. So this is a E1 voltage which is induced Vm sine omega t, then this is my corresponding to the 90 degree what I am getting, this is my peak value. So based on what is my peak value, peak is equal to Vm. So this Vm can be given in form of RMS value. So the peak value can be converted to the RMS value is equal to peak value divided by root 2. So this is equal to phi m omega n1 divided by root 2. So this can again be written as 2 pi f phi m n1 root 2. So 2 divided by root 2, 2 divided by root 2 is equal to this will come close to 4.44 f phi m n1. So this is what is my RMS value of the voltage induced, and the peak value is given by the Vm, and the instantaneous value of the induced voltage is given by E1 and E2, and this is the transformation or the turns ratio. Again it is seen that my n1 upon n2 is equal to E1 upon E2 is equal to A is a transformation ratio so if I am having if my primary ampere turns is, or the primary MMF is equal to n1 I1, and if I am connecting the secondary to a load, and the secondary MMF current is I2 and the secondary MMF is N2 I2. So in ideal case, since there is no loss, we can say that N1 I1 is equal to N2 I2. That is, whatever is MMF which is available at the primary is also available at the secondary, since there is a no loss case which we are considering for the ideal transformer. So it is possible to say that N1 upon N2 is equal to I2 upon I1 is equal to the A, which is equal to the transformation ratio. So this is a transformation ratio. So what do you have? here is the transformation ratio in terms of current. So again, what is my, if I consider the case where this transformer is having some kind of a impedance, it will be is equal to r square plus z xl square, but is equal to z square. If I consider the case of an impedance which is present for this transformer, and in the ideal case the impedance will be close to 0, but if I am considering the transformer is not ideal and I am adding some kind of a resistance present for the winding and some kind of a leakage reactance or the self inductance of each of the coils, which can be shown by the XL or leakage reactance, then it's possible that my Ohm's law VIR for this will can be shown by VIZ. So whatever is my V by V1 by Z1 or E1 by Z1 will be equal to, or V1 by Z1 will be equal to I1, and V2 by Z2 equal to I2, and in this case V1 by V2 will be equal to my transformation ratio A. So if I am considering that it's possible to show whatever is my secondary, whatever is my impedance at the secondary, that is the R and the XL, if I want to transfer to the primary side, so whenever I am connecting to a source, so the primary will be needs to supply for what is the loss at both the, even at the secondary, or it needs to supply for the inductance at the R or XL whichever is present at this side also. So it's possible to transfer it in a way as how the primary will, how it will be seen at the primary, and it's possible to do that in the ratio of the transformation ratio, so that my Z1 is equal to I1 upon V1 and my Z2 is equal to I2 upon V2. So my Z1 upon Z1 upon Z2 is equal to I1 V1 into V2 I2. So which is very much equal to, what is my I2 by I1 is equal to A. So this will be equal to 1 upon A square. So my Z1 upon Z2 is equal to 1 upon A square. So if I want to transfer my Z2 is equal to A square Z1, so when I am seeing this from the primary side, it's possible to move my impedance from the primary from the secondary side to primary side by multiplying it in the ratio of what is known as the transformation ratio. So this is the third thing which we have derived. This is the first thing which we derived, and then the equations, and this is a third thing. So this will be very much useful in case of considering for the equation or constructing the equivalent circuit for the transformer.